Hello there. I'm going to go over the answers to worksheet 1 and try to provide you some tips so that you do well as we progress here. Not too surprisingly, you should be open to worksheet 1, which I'm sure you completed for your homework. I think it's on page 95, maybe 94. I'm not quite certain off the top of my head. And of course you have a periodic table because, chemistry. Before we get into the answers, which are on the next page and things like that, before we get into the answers, we need to just remind ourselves that there are 3 categories for naming. There's ionic rules, molecule rules, and acid rules. And these 3 categories are defined by what sort of elements are in the combination of atoms. So remember, there's this dividing line that separates the 2 sides of the periodic table from the metal side and the non-metal side. It's separated by kind of a zigzaggy line right there. And if you have elements, say you have 2 non-metals, if you have 2 non-metals, that is what we call a molecule. So that would be 2 non-metals. If you have a metal and a non-metal, then you have an ionic metal, non-metal. And if you have something with hydrogen first, so hydrogen and then something after that, it is an acid. So let's take a look at these examples. This one would be an acid, starts with hydrogen. This is phosphorus and chlorine. Those are both nonmetals, a molecule. And this is cobalt and chlorine. Cobalt's a metal, so that's ionic. And then their names follow the same pattern. Cobalt and chlorine, ionic. Phosphorus and chlorine, molecule. And then acids are very easy to identify. The name literally says acid in the name. Okay, so we're going to start off with the ionic rules and work our way through some of the questions with ionics. Notice that I have a periodic table available. Our ionics are between metals and nonmetals, or metals and a polyatomic ion, and they have a charge, so because they're ions, they have charges. We have to use those charges to figure out the formula. So you go to the periodic table and you find the elements. So I found potassium, found fluorine. Fluorine's in the -1 column, potassium's in the +1 column, and wrote that down so that I could figure out the formula using their charges. So potassium loses 1 electron, fluorine takes 1 electron, and only takes 1 of each to satisfy the charge balance. Whereas in number 2, since lithium can only lose 1 electron, that's not going to be enough to satisfy sulfur. But if there was another lithium, or 2 lithiums could satisfy the sulfur. So it takes 2 lithiums to satisfy the sulfur. And it's not uncommon that whatever the charge is for one element goes and switches to the subscript for the other element, and then the charge for the anion becomes the subscript for the cation. Very common to just switch them. Silver's a +1, chlorine's a -1. We actually wrote silver was a +1 right on the periodic table last class, and therefore since that's a +1 and a -1, they already balance. Ammonium. Look as hard as you like on the periodic table, you'll never find ammonium, because ammonium is a polyatomic ion, NH4 +1. If it's a +1 and chlorine's a -1, that's not bad at all. Sodium oxide. Sodium's a +1, oxygen's a -2. Each time I'm going to the periodic table and I'm looking up these charges. So if sodium's a +1, there's going to have to be 2 sodiums to make that oxygen happy. Nitrate. And then after that is sulfate. these two are both polyatomic ions. Magnesium's a +2, nitrate's a -1. That means nitrate only takes 1 electron, but magnesium gives off 2. So magnesium would have to give away electrons to 2 nitrates. So here's how we do that. You see how the nitrate is in parentheses there? We'll actually make those parentheses pop just a smidge more. Okay, it's just a smidge. Made them pop a little bit, so there's 2 nitrates and 1 magnesium in that formula. And then aluminum sulfate. Aluminum's a +3, sulfate's a -2. If aluminum gives away 3 electrons, the sulfate can only take 2 of them. So it's going to take an interesting combination. Again, you can start off by just taking this charge and switching it there, taking that value and switching it there. See, the 2 and the 3. What's really going on there is you have the +3 charge, and there's 2 atoms, so that's 6 electrons lost. And you have the -2 charge, and there's 3 atoms, and they're gaining the 6 electrons. So the aluminum is losing 3, and the sulfates are gaining 2 each to balance each other out. So with ionic compounds, we have to grab the charges using the periodic table every time, and then we balance them out. Wait, there's more. So we have potassium nitrate. Potassium's a +1, nitrate's a -1. Pretty straightforward. Ammonium's a +1, carbonate's a -2. I'm going to need 2 ammoniums. Notice that the parentheses on ammonium is appearing, but there isn't a parentheses on carbonate. It's totally okay if you want to put, oops, that's not what I meant to do. If you want to put, that's still not what I want to do. Running on all cylinders here. If you want to put parentheses around that carbonate, that's totally fine. I hope you guys are enjoying this episode of Low Energy Murphy. Not exactly moving at all at full capacity. Well, even that didn't come out right. Okay, so iron, Roman numeral 3. What the heck is going on with these next couple of questions? Look at these guys. They all have Roman numerals in them. Well, up until this point, like when I did this potassium, for potassium, I just looked at the periodic table, found potassium. Potassium's in the +1 column, and it was pretty straightforward. When you look up iron or copper or any of these others, you're going to be in this middle area of the periodic table, and that middle area doesn't have common charges. We talked about this in class. If it has a Roman numeral, we're just telling you the charge. So that's what's going on the next couple, is they're telling you chromium's a 3, acetate's a 4, cobalt's a 2, copper's a 2, iron's a 3. They're just telling you the charge right there in the formula. And now that I have the charges written down, remember, sulfur is sulfide, chlorine is chloride. This ends in ATE. ATE, those are polyatomics. And so we just use the charges and kind of put things together afterwards. If that's a 3 and a 2, it's going to be a 2 and a 3. Get that? 3, 2, 2, 3. They swap. This is 2, 1, so the next one is 1, 2. That's 2, 1, so 1, 2. Again, since there's a 2 chlorates, you got to put them in parentheses. This is 4 and 1, so the answer is going to be 1 and 4, with the 4 on the outside of parentheses, so that all of the acetate is times 4. And then since that's 3, 2, it's going to be 2, 3. That way the electrons are balanced. And now we have to remind each other that we're going to name some stuff. When you name things, the metal goes first. You don't really have to do anything with the metal unless it's a transition element. If it's a transition element, you have to work out the charge. So it gets pretty straightforward. You just write down the name of the metal. So this is barium, so I wrote barium. That's oxygen. If it is a regular nonmetal, not a polyatomic or something like that, if it's just a regular boring nonmetal, like oxygen, sulfur, fluorine, we're going to change the endings to IDE. So here we have the first three are pretty straightforward. I wrote down the name of the metal, barium, potassium, calcium. Then I changed the nonmetal to IDE. What is going on in number 18? There are too many elements. Same thing in number 19. Too many elements. If you have 3 or more elements, there's a polyatomic ion in the formula. Make sure you look at it carefully to find the polyatomic. What polyatomic is in 18? What polyatomic is in 19? So we have potassium and NO3. NO3 is nitrate. We have magnesium and CO3. CO3 is carbonate. Magnesium carbonate. We have silver and oxygen, so that's silver oxide. Number 21 is just about as hard as number 19. Magnesium carbonate again, those of you playing along. And then we have zinc chloride and ammonium phosphate. Again, too many elements, way too many elements. Definitely some polyatomic ion action going on in there. And I just want to point out, this is also, I'm going to throw parentheses here and a 1. This is still that the 3 and the 1 are being used. So the 3 and the 1 switched places to make that formula. And I bring that up because we have an element here that's in a weird column, SN. SN is in this weird column. It's not really following the rules. So we're going to have to figure out its charge. SnCl2. We know this is a 1. And if I go to the periodic table, I see that chlorine is a -1. So if this is a 1,1, then this must be a +2. So we're going to say that element 10 has a +2 charge, Roman numeral 2, and it's with chlorine chloride. Yeah. That's what's going on in the next one also, is the cobalt and chlorate are together. One cobalt, and chlorate is a -1, so that must be a 2. Yep. Take a guess at what gold's charge is in number 26. You guessed it, it's a 3. And PT, physical training, no, platinum, right. Platinum is going to be a 4, as it's with chlorine that time. Always check the charges, though. If that had been platinum and oxygen, 1 platinum, 1 oxygen, go to the periodic table, find that oxygen is a -2, well then platinum has to be a +2. If platinum loses 2, oxygen's gaining 2. Make sure you check the charges on the periodic table. Oh, let me just make sure that you can all see those answers down there at the bottom. I guess you could have paused it or gone back or whatever, but you know, I don't want you to have to work too hard pushing buttons and things. Okay, we have switched categories. We are now on the molecule side, remember molecules are two non-metals. These are actually way easier to do. They have prefixes in the name, mono, dry, tetra, blah, 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 and those prefixes tell you how much of each element is there. So triphosphorus and octaoxygen would be 3 phosphorus, 8 oxygen. The only rule that's kind of funky is mono only gets used on the second word, it never gets used on the first word, and they changed the second word to IDE also. Arsenic and diiodide, that'd be arsenic and 2 iodines. 1 and 1, 1 and 3. Tetra means 4, mono means 1, and so forth and so on. I'm just going to let you take a look at those. Use the prefixes to make the name. Hey, what about the charges? Stop. Stop, stop, stop. Molecules don't have charges. Molecules are sharing electrons. These are covalent. They're sharing electrons. If we wrote a real formula, then you should be able to draw a Lewis dot structure and be like borons in the middle, connected to 3 fluorines, blah 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 blah, with all the dots and stuff. These are following those rules, the octet rule, and things like that. You don't need to worry about charges because they're sharing electrons. And now time to reverse it. Again, you use the prefixes. If it's a 2, use the prefix di. If it's a 4, use the prefix 4. 4. So that's 2 carbons, dicarbon, 4 chlorines, tetrachlorine, and then we change the second word to IDE. So dicarbon tetrachloride. Dinitrogen monoxide. Tetraphosphorus hexaoxide. Usually hexaoxide. Hexoxide is also hard to say. We're going to talk about style here for a second. I really want you to try your best. You take the hexa, put it in the front. Take the oxygen, you put it afterwards. You change the oxygen to an IDE, and you're trying to assemble it to the best of your ability. The more you practice this stuff, the more likely you are to get closer and closer to the accepted way of saying some of them. Hexaoxide just kind of sounds weird no matter what. But there you go. Trinitrogen, 3 nitrogens, monoiodide. You don't get to put 3 vowels next to each other often enough. And then 8 silicons, octasilicon, pentafluoride, and sulfur trioxide, which is really dangerous. And our third category, yay! Acids. When we deal with the acids, we also have to deal with charges, but dealing with charges is a heck of a lot easier with acids, because we'll always have hydrogen first, and hydrogen has a positive 1 charge. So when we go to put the charges together, and we put the 1 here, we take the other charge, put it there, it's pretty easy to deal with because the hydrogen only has a +1. And maybe we'll have multiple hydrogens, but we don't have multiple of the anion. We just have multiple of the hydrogens. So we do have to do the charge thing here. Oh, this eraser is really ineffective. Oh, should he leave just a little piece there? That would be mean. That's not like me, so I'm going to erase it. There we go. That's better. There we go. And then the rule I taught you guys in class was this silly phrase. It was 8-ic, 8s, hydroblankic. So let's see if we can find an example of each one here. Here we have an ick, an us, and here we have the hydro and the hydro. So these three rules, are there more? Yes, of course there's more. Another us, another hydro. These three rules mean that the icks are actually nitrate, sulfate, and the ites are actually chlorite. And I mean the us's are chlorite and phosphite. And then with the hydro, so the icks are actually eights, the us's are actually ites. And then what do we do with this hydroblankic? Well, we have to carefully analyze what is in the blank. So here it looks like it's chlorine. Here it looks like it's sulfur. And this is cyanide. Oh, cyanide. That's cyanide. It's one of those polyatomic ions somebody asked to memorize a while ago. So let's go put this stuff together. We need a periodic table. Let me grab one. Boom, periodic table has appeared. So, hydrogen has a +1 charge. And then chlorine is over here in that -1 column. And so chlorine is a -1 charge. So that's just going to be HCl. No problem there. Hydrogen has a +1 charge. Sulfur's in the -2 column. So that's going to be -2, which means it's going to be H2S. And then we have hydrocyanic. Hydrogen has a +1 charge. Cyanide is a polyatomic ion, Cn-1. So this is HCN. Now we need to do these polyatomics. Let's just switch colors for fun. Hydrogen is a +1 charge, and nitrate is NO3 -1. +1s and -1s balance out, so that's HNO3. Let's see, sulfuric is actually sulfate. Hydrogen has a +1 charge, and then sulfate is SO4 -2. So since sulfate's a -2, it's going to take 2 hydrogens to go off the right amount of electrons. And then chlorite, let's just draw a line here. There we go. Chlorite and phosphite are ites. And you did not have to memorize the ites. You had to memorize a bunch of eights. So you're going to look on the back of your periodic table. You can find chlorite is ClO2 -1. And phosphite is PO3 -3. And they're both with hydrogen has a +1 charge. Hydrogen has a +1 charge. That's the level of energy I've got right now. You're getting the best right there. And so we put these together. The hydrogen and the chlorite, and the hydrogen with the phosphite. And again, that 3 means there's got to be 3 of these, and there's got to be 1 of those as you switch them. Since there's only 1 PO3, there's no reason to put parentheses. Same rule, but in reverse. So we've got to look at these things and figure out which rule is being applied. That is not what I meant to do. This is iodine, so we're probably just going to use the blank. This is nitrogen, we're just going to use the blank. This is phosphate, we're going to use the 8 to ic. This is chlorate, we're going to use the 8 to ic. This is sulfite, we're going to use the ite to us rule. Let's just move this out of the way and perhaps erase everything. Yep, that's everything. And then this should be hydroiodic acid. There we go. You know what? I'm going to do you all a huge favor. Huge. I'm going to show you my fantastic typing skills. So hydroiodine becomes iodic and then acid. And then nitrogen, let's see, nitric, there we go. Hydronitric acid. That's phosphate. 8's become ic. So phosphate. We drop off. Oh, come on. That was classic, wasn't it? Drop off the 8. It's totally okay if you write phosphic, but most people write phosphoric acid. Oops, dyslexia. So again, with the make it slightly bigger. Won't have to squint at it as much. Boom. That's not terribly better. There we go. So with phosphorus and sulfur, you'll often see this OR or UR kind of squeezed into there to make it sound somewhat better. So phosphoric is really common, sulfuric is common, sulfurous, phosphorus acid. But right now I'm just making sure you get from 8 to ic and ite to us. So this one is chlorate. I'm going to drop the 8 and replace it with an ic and acid. And the last one is, on the back of my periodic table, is sulfite. And I drop the ite, and I can say us, sulfus, or sulfurous. And sulfurous is the commonly said way of it. Again, I'm happy with either one of those. I had a typo right there. It's probably been bothering someone. Hydroiodic acid. Okay, them's the rules. 8 ic, itis, hydro, blank ic. Use the charges to balance out the hydrogens. Mono di, tri, tetra, penta, hexa, octa. Anytime you have two non-metals, you get to use prefixes. And if you have just metals and non-metals, we use the ions. Alright, ladies and gentlemen, I'm going to do a video now on the Chemicals Around Us project. Look for that.